Hello and welcome back to Principles of Statistics. In Chapter 4, we will be learning about probability. These are the concepts we will learn. First, we will look at experiments, how to count outcomes according to certain rules, and how to assign probabilities to those outcomes. Then we will look at the notion of events and how to calculate their probabilities. Finally, we will look at some basic relationships of probability. In life, we usually face uncertainty when making our decisions. For example, what are the chances that it will rain tomorrow? Or, what is the likelihood that I will pass this course? Or, what are the odds that stock prices will reach a new high in October? As you will note, each of the above questions that we looked at in the earlier slide implicitly have the notion of probability behind them. What is probability? It's just a numerical measure of the likelihood that an event will occur. If an event is sure to happen, its probability is 1. If it's almost certain to happen, then its probability will be close to 1. On the other hand, if an event will never happen, then its probability is 0. And if an event is very unlikely to happen, then its probability will be close to 0. Hence, probability ranges from 0 to 1. So this is the way we can look at probability. It's a measure, a numerical measure, of how likely an occurrence is to happen. A probability of 1, it will definitely happen. A probability of 0, it will never happen. A probability of 0.5 that it will happen is just as likely as that it will not happen. Let's not look at the notion of an experiment. An experiment is basically a trial, or something that you do. And each experiment can have at least one outcome. Consider the experiment of tossing a coin. There are 2 possible outcomes. You get heads, or you get tails. Considering an inspector who is inspecting the parts of a factory. When he or she looks at a particular part, there are 2 possible outcomes. 1, the part is defective, or 2, the part is non-defective. When a salesperson knocks on the door trying to make a sale, there are 2 possible outcomes. 1, there will be a purchase, or 2, there will be no purchase. If one rolls a die, there are 6 possible outcomes. You could get 1 or 2 or 3 or 4 or 5 or 6. And when a football game is played, there are 3 possible outcomes. Win, lose, or tie. What are the possible outcomes when one plays roulette? Please take a moment and think about the answer. Let us now look at the notion of a sample space. Consider this particular example. Bradley is investing in 2 stocks, Markley Oil and Collins Mining. For each stock, these are the possible outcomes. For Markley Oil, one outcome is that there will be a profit of $10,000, or $5,000, or 0, or a loss of $20,000. Hence, for Markley Oil, there are 4 possible outcomes. On the other hand, for Collins Mining, there are 2 possible outcomes: a profit of $8,000 or a loss of $2,000. This is the so-called counting rule for multi-step experiments. Think of it as if there are several steps. In the first step, you will observe the outcomes. After you have observed that particular outcome, you will then do the next step. Hence, if there are n1 possible results for the first step and n2 for the second step, then the total number of outcomes for a two-step experiment will be n1 times n2. If there are k steps, then the number of experimental outcomes will be n1 times n2 times n3 all the way to nk. One way to think of this is that there is a tree diagram. So, going back to the Bradley investment, you can think of it as a two-step experiment in the sense that the first step will be, let's see what happens to Markley oil. There are 4 possible outcomes, right? Having then observed what happens to Markley oil, we will then observe what happens to Collins mining. And there are 2 possible outcomes for that, as you will remember. Hence, there will be 4 times 2, or 8 possible outcomes. Consider these tree diagram. As you can see in the first step, there are 4 possible outcomes: a gain of 10, a gain of 5, a gain of 0, or a loss of 20. What happens now? Suppose we've gained 10 with Markley. There are now 2 possible outcomes to our investment in Collins. We will gain 8 or lose 2. Hence, if we follow this all the way through, look at the first branch. It will be a gain of 10 from Markley and a gain of 8 from Collins, for a total gain of 18. But another possibility is a gain of 10 from Markley and a loss of 2 from Collins, for a net gain of $8,000. Now consider, suppose we had gained 0 from Markley. This is the third branch in the first step. If we now observe what happened from Markley, there will now be 2 possible outcomes afterwards, which is gaining 8 from Collins or losing 2 from Collins. And as you will see, in the first case, 0 plus 8 is a gain of 8. In the second case, 0 and the loss of 2 is a net loss of 2. But be careful. Don't think of this literally as you invest in Markley first, look at the result, and you invest in Collins second, then look at the result. Of course, these 2 things happen together. Here is an experiment. Why don't you do the tree diagram, but make Collins the first step and Markley the second step? Prove for yourself that there will still be 8 possible outcomes and that the possibilities will be exactly the same as in this diagram. Now, this tree diagram has been fairly easy to draw because there were only 2 steps and there were only a limited number of outcomes for each step. Things will become more difficult if we have lots and lots of steps or a lot of outcomes for each step. That's why it will be helpful to learn the so-called counting rules. Let's look at combinations. What is a combination? A combination is when you take n small objects, it's when you take small n from a larger set of big N, and you want to count the number of outcomes where the order does not matter. So for instance here, if an inspector selects 2 of 5 parts, we are interested in seeing what pairs could he get, and if he gets first part C and then part B, that's the same as getting first part B and then part C. So let's go back to this slide. This is the formula for counting the number of outcomes in the case of combinations. Please take a moment to consider it. In the numerator, you will see n and an exclamation point. That is a mathematical operation. It means big N factorial. Whereas in the denominator, you will see small n factorial and a parenthesis big N minus small n and then factorial. The way to think of this is, suppose big N is 5. Then big N factorial or 5 factorial will just be 5 times 4 times 3 times 2 times 1. What is 3 factorial? 3 times 2 times 1. What is 1 factorial? 1. What is 0 factorial? 1. So, let's go back to this example. An inspector randomly selects 2 of 5 parts. How many combinations of 2 parts can come out? That is, we don't care about the order. CB is the same as BC, AB is the same as BA, CE is the same as EC. Let's use that formula. The formula is big N factorial in the numerator divided by small n factorial times big N minus small n factorial. Hence, that will be 5 factorial divided by 2 factorial times 3 factorial. Whereas you will see the numerator is 5 times 4 times 3 times 2 times 1. And the denominator is 2 times 1 times 3 times 2 times 1. All of these add up to 10. You could have gotten the same result by writing down all possible combinations. And this is what we see at the lower half of the page. So you could get AB, AC, AD, or AE. You could also get BA, but we don't care about that because BA is just the same as AB. Remember, we don't care about the order. So you could also get BC, BD, and BE. But remember, we don't care about CB because it's just the same as BC. And so on. As you will see, there are 10 possible combinations. But what if we care about the order? What if we care that so that AB is not the same as BA? What we then use is the counting rule for so-called permutations. With permutations, we get a number small n from a larger set big N, and the order of selection is important. Please take a moment to consider the formula. As you will see, the formula is big N factorial divided by big N minus small n factorial, where again the factorial operator is the same as in slide 10. So let's consider the case again of the inspector taking 2 out of 5 parts. But now AB is not the same as BA and should therefore be counted differently. Hence the formula is big N factorial divided by big N minus small n factorial. And big N is 5, small n is 2. So if you look at the formula, we will get 20 possible permutations. As with slide 12, the long way to get the above result is to write down all possible permutations, which you will see in the lower half. AB, AC, AD, AE. And note that AB is not the same as BA. Note that AE is not the same as EA. Obviously, this will become difficult or even impossible if the big N's and the small n's are quite large. Hence, It's better to remember the formulas for permutations and combinations. Why don't you try this problem? What if you take 3 from 10? What are the number of possible combinations and the number of possible permutations?